Hello everyone, welcome to Mostly Math. Today I'll be giving you a few examples of how we can use the General Leibniz rule. This rule allows you to differentiate the product of two functions n times. It states simply, if you want the nth derivative of a product of two functions, you can do this as long as you know the nth derivative of the original functions and the binomial coefficients. Now this may look pretty scary because we have a summation, coefficients, and various indices. Also, you may see these written the other way as well. In most literature, it could be n minus k g of k. This is totally fine since the binomial coefficients are actually symmetric since they come from Pascal's triangle. You know, it's 1, 1, 2, 1, and then we got 3, and so on and so forth. And an example of this formula is the second derivative formula. We had two functions multiplied together. We wanted the second derivative. It would tell us that this is simply f times the second derivative of g plus 2 times the first derivative of f, first derivative of g, plus second derivative of f times g, which is totally cool. We're using this row of Pascal's triangle. And it also tells us that if we had the third derivative, for example, triple prime, well, we'd have fg triple prime plus this coefficient, f1 g2 plus 3 f2 g1 plus f triple prime g. That's what it would tell you. It's really not very scary. It just tells you that look at Pascal's triangle, take the nth derivative of the functions, and that's how you can get the nth derivative of the product. It's very straightforward. Let's go ahead and look at a few specific examples. So in this video, I'm not going to be proving this statement. I'll do that in a subsequent video. This is more of an applied video. I just wanted to show you why the formula is useful before I show you a bunch of proofs about it. So our first example to illustrate this is going to be second derivative of sine x e to the x. Okay, here's how you do this in practice. We are going to make a table of derivatives. We have n, 0th derivative, calling this one sine, and this one e to the x. And first derivative we'll take is cosine x, and e to the x still. Second derivative is minus sine x, and e to the x again. So just 0, 1, and 2 derivatives, that's all we need. We also need Pascal's triangle, just this row here, 1, 2, 1, which gives us the binomial coefficients. And in practice, what this formula says here is if you want the second derivative of the product of two functions, you're going to make this table. You're going to take this function at the left-hand side and this function at the right and multiply them together with the weight of the binomial coefficient. So this allows us to write down immediately the following answer. Binomial coefficient of 1 of sine x e to the x plus binomial coefficient of 2 of cosine x e to the x, and then a 1 times minus sine x e to the x. See, we have a cancellation, and our answer is 2 cosine x e to the x. So with this particular example, this derivative isn't actually that hard. Feel free to evaluate it yourself. It'll be about the same amount of work. I just wanted to show you the most basic example of I knew about how you can use this formula. All right, let's look at a slightly different function. Using some more rows of the binomial coefficients. Okay. Next example is the following. The third derivative now of x cosine x. Okay, let's make the table just like before. Not very hard. N. 0, x, and cosine x, 1. It's going to be 1 and minus sine x. 2, we're going to have 0, and sine goes to cosine, so this is minus cosine x. And finally 3, this is still 0. Cosine x goes to minus sine x, so we're back to sine x. And this example shows you the true utility of the formula. If you have a situation where after a certain number of derivatives, one of the factors becomes 0, you can simplify the result significantly by starting at this end of the table and then only keeping the first two terms because the other ones are 0. Making sure I did this right. Sine goes to cosine. Yep, this is right. Okay. So we start at this end of the table. X sine x. Oh, sorry, I almost forgot the triangle. So we need 3. Yeah, we need this row of the table here. Okay, so we do these two. We multiply these two with a weight of 3. And if we had continued on, these would be 0. So we're actually done. This is the answer to this problem. That's it. Now this one, if you try it by hand, it is actually kind of a lot of work. Feel free to try it yourself and let me know which method you like better. All right, let's step it up a notch. Let's now talk about a fourth derivative. So we're going to add another row to our Pascal's triangle here. And we add these together and get 3 plus 1 is 4. Sorry about that. So we have 3 plus 1 is 4, 6 here, and then 4, and then we get a 1 there. So now we're going to use this row of Pascal's triangle to talk about the fourth order derivative I'm going to demonstrate for you. Okay, and we're going to be discussing the fourth derivative of x e to the x. Let's make the table like before. Make our table. And we have 0, so x e to the x, 1, 1 e to the x, 2, 0 e to the x, 3, 0 e to the x, and 4, 0 e to the x. Again, notice the redundancies. Notice the zeros. All right, let's do it to it. We all know how to do this now. This end and this end. So we have x e to the x plus e to the x times the binomial coefficient that's next, which is 4. And we could just go ahead and factor out the e to the x here. X plus 4 e to the x. And this problem is nice because it allows you to very straightforwardly generalize to n. So, just for example, if we let 4 go to n, dn by dxn of x e to the x will simply be x plus n e to the x. So even if you don't evaluate it from the beginning with n's, you can sometimes in very simple situations, you can pretty much guess what it's going to be. And this is correct. All right. Let's go on to our next example where we do indeed start from the nth derivatives from the beginning. Try to evaluate that. Oh, incidentally, one use of this, the main use is, let's say your friend asks you a trick problem, you know, what is the 100th derivative or something, or the 20/20th derivative, like you might see on some kind of a math exam, like the Putnam or something of x e to the x. Well, instead of differentiating this 2020 times, you just have to put 2020 here, and there you go. Pretty great, huh? I think this is cool. In fact, one of the uses of finding the nth derivatives is if you had a trick problem like this on an exam where you had a high number of derivatives, you'd have to evaluate the nth derivative anyways to find it. All right, continuing. All right. Next example is the nth derivative of x squared e to the minus x. I'm just getting tired of putting e to the x, so I put you a minus sign there for some additional variety. Okay, so now we are going to do what we did before. I'm going to have a table. Start with 0, which is x squared e to the minus x, 1, which is 2x minus e to the minus x. And basically every time we differentiate the e to the minus x, here we're just going to put a minus 1 outside. And second derivative becomes 2 e to the minus x, 3, finally goes to 0, e to the minus x. And this will continue on n times till we have 0 and we have minus 1 to the n, e to the minus x. So if you have an odd number of derivatives, you're going to have a minus x. If you have an even number of terms, you're not going to have a minus x. Okay, now the binomial coefficients. We're going to not draw the triangle because it's not really going to help us. We're just going to evaluate them using this formula and choose k is equal to n factorial over k factorial n minus k factorial. Very common way to do it. I'll see if I use that formula. Either way, it's good for you to know. Okay, so we're going to start off at this end of the table and this end of the table and just multiply things together. All right, so we're going to have x squared times minus 1 to the n e to the minus x. That's the first term. I'll write the n choose 0 just to make it more explicit. N choose 0, which is 1, according to this formula, or you can just know from the triangle that it's 1. And now we have n choose 1. Okay, now we have 2x. And we have the previous term here, which is minus 1 to the n minus 1, e to the minus x. And we get one more term in our expansion, plus n choose 2 times 2, negative 1 to the n minus 2, e to the minus x. And now we just have to evaluate this binomial coefficient here. It's not too hard. So n choose 2 simply equal to n factorial over 2 times n minus 2 factorial. And this is n minus 1, n minus 2 factorial over 2, n minus 2 factorial. These cancel, and we get n minus 1 over 2 for n choose 2. And we know that n choose 1 is n because you just know it. Feel free to use this formula if you don't believe me. And now we have everything we need to know here. I'm also going to simplify the minus 1 to the n's here. We're going to use as well. Yeah. So we have minus 1 to the minus 1 power is just 1 over minus 1, which is minus 1. We also have minus 1 to the minus 2 power is just going to be 1 over minus 1 squared, which is 1, of course. So this allows us to factor out the minus 1 to the n. So we're going to have a minus 1 to the n factoring out, have an e to the minus x factoring out. And this is just going to be x squared plus 2nx, sorry, minus 2nx. And this, okay, so we have 2 times n choose 2. So the 2 here at the bottom goes away. It becomes n minus 1. And is that it? At this point, I'm going to check my notes to make sure. Minus 1 to the n, e to the minus x, x squared minus 2nx plus n minus 1. Yes, we are done. This is the nth derivative, and now we can celebrate by plugging in, say, the 100th derivative. If you were giving this on an exam or something, of x squared e to the minus x. This is actually a very common problem in textbooks where you can find this rule applied, such as mathematical methods books. Okay, n equals 100. So it's just going to be minus 1 to the 100 is not there. E to the minus x. We have x squared minus 2 times 100, which is obviously 200. And plus 100 times 99, which is obviously 9900, right? There you go. I just want to show you an example where we get down to the straight numbers that everyone can appreciate. Pretty sure I did that right. I think it's right. If it's not, it's close enough. Okay, now we could go on to the pièce de résistance. So basically, before recording the video, I knew how to do everything that I've shown you how to do so far. But I did not know how to do what I'm going to show you next, which is pretty cool. Let's get to it. So my next thought was, how can we generalize this? What if I had derivatives of, say, x to the 7th, e to the minus x, and so forth, and I wanted to take the nth derivative of that. I don't want to have to go through all the work that I just did with this table. Instead of doing it for every power of x that I multiply e to the minus x by, there has to be some way that I can just keep them all together. Well, there is a way. I will show it to you now. Okay, people, let's get it going. Right. So now we are going to conquer following bad boy. We're going to have the nth derivative of x to the m e to the minus x. Well, so many letters, so scary. No, it's not scary. I just don't want to have to do this every time for x to the 9th e to the minus x and x to the 11th e to the minus 6. So I just want to do it once. That's why I'm writing m. Unfortunately, if I want to be more general, I have to tell you more equations that I'm going to use. So we are going to note the following derivatives. So we're going to use these derivatives. We obviously had the, I'm gonna call them k for reasons that you'll see. The kth derivative of e to the minus x is just minus 1 to the kth power e to the minus x. Next the nth derivative. I don't know. Okay, so now we also need to know that the kth derivative of x to the n is equal to n factorial over n minus k factorial x to the n minus k, which is the same thing as k factorial n choose k x to the n minus k. Maybe you haven't seen this formula before. I'm not going to derive it for you now. It can easily be done by induction. But just so that you believe that it's true, an example, the second derivative of x cubed. This one should be non-zero. Well, it should be 3 factorial over 3 minus 2 factorial, which is 1 factorial, x to the 3 minus 2, which is 6x. So you should believe that it's true, at least, since it holds in this one special case. And also note, it tells us that, say, if we had the third derivative of x squared, this will be 0. So this formula is only valid for k less than or equal to n. It's going to be 0 for k greater than n. This is very important. Very important. Okay. 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 Let's do it. Okay, everyone. Now, in this pièce de résistance, we're not going to draw a table. We are just going to apply the formula directly in all of its glory. So we can see that all these sums and binomial coefficients are not scary. They're not scary. Okay, using the formula directly, this thing in here, this big thing in here that we've been talking about the whole time, is equal to sum k goes from 0 to n. N, choose k. We have the kth derivative I forgot a k up here, sorry. dk by dxk of, I'm going to call this first thing f. X to the m goes first. And now we have the n minus kth derivative of e to the minus x. Well, this is pretty straightforward. We have the sum k equals 0 to n, and choose k stays there. We now have, from this formula, k factorial m choose k, because x is to the nth power, x to the m minus k. And now we have a minus 1 to the n minus k, e to the minus x. And now we're going to simplify a few things here. We are going to note that we don't actually have to sum it up to n. We can actually stop at m because of this condition that we talked about here. Oh, first I'm gonna take out a few things. So e to the minus x is always there, and negative 1 to the nth power is always there, just like before. Negative 1 to the n, e to the minus x. And now we have the sum k equals 0 to m, and we have our k factorial. We have m choose k, and we have n choose k, and we have x to the m minus k. Let's see if I did this right. Excuse me. Let's see if I did this right. So I've been working on this for a long time. I have lots of work about this. Hard to find everything. Well, that's strange. I can't seem to find it, but I think it's right. I think it's right. Oh no, I did forget one thing. I always forget this. Minus 1 to the k factorial. Okay. And now I will attempt to show you an example of this. I'm pretty sure this is right. Let's see if I can show you guys an example. Our final result is minus 1 to the n, e to the minus x, sum k goes from 0 to m, minus 1 of the k factorial, m choose k, n choose k, x to the m minus k. Okay, example time. So this is a pretty stupid example since I could easily get this by differentiating what I had before. But I'm going to show you the very next term in the sequence. We are going to discuss the following derivative. I'm going to derive this one, the nth derivative of x cubed e to the minus x using this formula. Okay. Minus 1 to the n, e to the minus x like before. Now, we're going to have 4 terms, k equals 0, 1, 2, and 3. So we have minus 1 to the 0. 0 factorial of, so this tells you that m is equal to 3, of course. Just want to write it there so I don't forget. 3, choose k. K? What is k? No, k is now 0. 3, choose 0. And n, choose 0. X to the 3 minus 0. And now we're going to have minus 1 factorial. 3, choose 1. N, choose 1. X to the 3 minus 1 is 2. And plus 3, choose 2. N, choose 2. X minus, last term. 3, choose 3, and choose 3, and that's it. All right, I really wish I had my notes about this one. Let me just take a quick look around, see what I can find. It is very strange. This is just demonstrating that you should be much more organized than me. I guess it is here, after all. And yes, I can confirm that I did it correctly. Make sure this is right before we proceed. Excuse me. I did forget some factorials. So we have 0, 1, and now I need a 2 factorial. And now I need a 3 factorial, which is 6. I do apologize. This is very tricky stuff. It's important to have your notes and to be much more organized than me. All right, now let's try to calculate what we can, and we'll stop when we get stuck. Minus 1 to the n, e to the minus x. So we know that 3 choose 0 and n choose 0, both 1. So the term is going to be x cubed. We know that this is 3, and this is n, x squared. And for this one, 3 choose 2. Well, we can calculate pretty quickly from the binomial triangle. Okay, so we got 3, 0, 1, 2, 3. And we have 3 choose 0 here, 3 choose 1, and 3 choose 2. So this is the answer that we seek. 3 choose 2 is 3. Plus 2 times 3. Then we have n choose 2 before, which is n minus 1 over 2 x. So it should become 3n n minus 1 x, which it does. And for the last term, excuse me, we now need 3 choose 3, which is 1, and n choose 3, which we have to calculate. All right, n choose 3 is n factorial over 3 factorial, n minus 3 factorial, which is n minus 1, n minus 2, n minus 3 factorial over 6, n minus 3 factorial. Bad boys go away. n minus 1, n minus 2 over 6. So the 6 conveniently cancels. Minus 6n, n minus 1, n minus 2. And that is correct. And that is, well, the 6 actually got canceled. That's correct. And that's all I have time for today, guys. These are some of my favorite examples of the General Leibniz formula. It's very useful both in making a table and by having the nth derivatives beforehand. Next video, I will show you some proofs about how you derive the formula in general. Now that you know how to use it, you might be interested as to why it's true. So please stick around next time. Like, subscribe, have a great day.